Okay, here we are at part 2, and it turns out that we can observe these properties. The angle of incidence equals the angle of reflection and virtual images in this slightly altered example. We're going to take a mirror, and the mirror is going to be spherical this time. So we're going to curve the mirror. So as you take notes, draw this with a little bit of size to it. And this is a spherical sorry, I just started the timer. A spherical mirror. Spherical mirror. So the spherical mirror will have if we were going to complete it, it would be a complete circle. So I'm just going to imagine the rest of the circle, but this part is a mirror, and the reflective surface is on this side, and the non-reflective surface is on this side. So when it's shaped like this, we call it a concave mirror. So this is the reflective surface on this side. The other side, on this side of the line, is the non-reflective surface. And we call it concave because the reflective surface is forming a little cave that we can walk into. So let's look at some properties of this spherical mirror. If we were going to complete the circle would have a radius. So it looks like it would be about right there. That point is important, and I'm going to call it R for the radius. It's where the radius would be. It's the center of the circle. I'm going to call it the radius point. Now we're going to draw a straight line through the radius to the mirror, and that line is called the optical axis. And again, I've got notes, so you've got notes, so continue on to your day 1 notes. In fact, we can actually add a topic before I forget. We have our little box started. We talked about reflection, and now we're talking about ray tracing. So you can add that to our topics for today 1. All right, we'll go for a little bit on ray tracing. All right, when we're tracing rays to a spherical mirror, they are going to obey the law of reflection. So the angle of incidence will equal the angle of reflection. So let's draw a light beam that's coming in horizontally to the reflective surface of the concave mirror. So this is a light beam, and it's coming in, and it's going to obey the law of reflection, but since this is rounded, we're going to use a tangent line, which you learned about in geometry and other places. And you calculus students talk about tangent lines quite a bit. Tangent line is a line that will touch the circle in one point, but it doesn't touch the interior of the circle. So this is a tangent line, and there's one tangent line at each point, and this light beam is striking the mirror, and we're going to observe the angle it makes with the tangent line. So we're going to observe that angle, and we are going to approximate that same angle as it comes off of the mirror. So say it comes off like that, trying to make the angles, this angle between the line, the reflected part of the ray, and the tangent line equal. So when we do that, we get a reflective part that comes like that. All right, let's take in another horizontal line. Let's say we take in one from this area. So it's going to go in and hit the reflective surface. Here's the tangent line at that point, and it's going to reflect similarly. And if we take in third line. I'm taking all my beams horizontally, so it's going to hit here and reflect like that. And if there's one that comes in through these words here, it's going to reflect like that. And you can probably see what's happening. All the light rays that come in horizontally to a concave mirror will reflect back through one central point. So hopefully your notes are reflecting that. So alter them if they're not, because that's what happens. And we call that the focal point. Right there is the focal point. And there's a relationship between the radius and the focal point. I usually call the focal point small f, and the radius we often call it capital R. And there's a relationship, and that is the radius is twice the distance to the focal point. So this is right in the middle. So one radius is the same as two focal points. So that's, if we know the radius, we can immediately find the focal point by going half the distance. And if we know the focal point, we can find the radius by doubling the distance. So usually the law is written like this: the focal point is the radius divided in half. So either way, it's stating the same principle. So moving right along, I will mention now that I fudged a little bit here. Do you know what I did? That wasn't particularly accurate. Well, it turns out that this principle here, creating this focal point from all the reflections, is not as precise with a spherical mirror. It is very precise with a parabolic mirror. So when the focal point really matters, like say on the Hubble Space Telescope or in a specialized microscope or camera, we should be using a parabolic mirror. A parabolic mirror is what really creates this effect. This focal point is a little bit off. The point, all of the rays that come in horizontally are not going to exactly hit this point. They'll be close. But if you have a parabolic mirror that acts like a parabola that you've studied in math class, it has a focal point, and you may have called it that in math class, the focus, and that is a physical point, because the rays come in a parabolic mirror and they precisely meet in one point, just like that. So mathematically you found different equations that allowed you to calculate that. We're not going to go to that extent here, but I want to say why I even brought up the fact that there are spherical mirrors if they have to be parabolic for this to happen. And the answer is this is quite easy to make, and this is quite hard to make. And this is quite inexpensive to make, and this is quite expensive to make. So where the focal point is very important, you do want to go through the extra effort and expense. But when it's not, this will do the trick, and it's quite easy and inexpensive to make a spherical mirror. So your focal point won't be as precise, as crisp as this one, but for most cases, or for many cases, this is fine. It works fine. So just want to bring that point up. All right, so let's do some ray tracing. To do the best ray tracing, you need to have a little bit of size to your drawing. And if you can't draw a straight line, get a straight line edge, a straight edge that can help you. A ruler, the side of a book, an index card. And I'm going to try without, but let's see how I do. All right, I'll set this up and probably shut down part 2 here to conclude on part 3. All right, so what I want you to draw, just for some training at this point, we're going to take a concave spherical mirror, and draw it. And I'm going to take an object that is sitting on the optical axis. So I'm going to draw an optical axis, the straight line there. And I know that the radius and the focus are related. So I'm going to go ahead and put the object that I'm putting in front of this mirror. Let's say it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Say it's 16 centimeters. These aren't true centimeters. They're just representations of equal units, and I counted off 16. So say an object is sitting at, and I always use my object as an arrow so I can tell where the top and the bottom is. Your object can be anything that has a clear top and bottom, so an arrow works very well. And let's say the radius of this is like 8 centimeters. 1, 2, 3, 4, 5, 6, 7, 8. So I'm told that this point is the radius. So I don't need to be told to focus because I know it's halfway. So I go 1, 2, 3, 4. So let's say the focal point is here. All right, to do a ray tracing, what I'm looking for is how the image appears in the mirror. And to finish that, we will go over to the next part.